Okay, hello everybody, and welcome to the last of the Physics 121 YouTube videos. Like I said in the last video, we have finished the material that will be covered on the exam, and so that was up to and including induced electric fields. And so this is just a bonus material for anyone who is potentially interested. So what I want to talk about today are inductors, and an inductor is just a solenoid. So we know some stuff about solenoids. It's just a coil of wire, and what we're going to do is we're going to pass a current through the coil of wire. Current is a source of magnetic field, and we used Ampere's law to determine the strength of that magnetic field, and it was equal to mu naught n times I divided by L, where L is the length of the solenoid and N is the number of coils or the number of turns in our winding. And by the right-hand rule, we could determine the direction of the magnetic fields, and the magnetic field for the solenoids that I've drawn here is going to point from the left edge of the screen to the right edge. And so there's our magnetic field. So the starting point is to calculate the flux through the solenoid due to its own magnetic field. So let's calculate the flux, let's say the magnetic flux. The magnetic flux through our solenoid due to its own magnetic field. In order to do that, what we need to do is we need to know the area of our solenoid, the cross-sectional area. And so we'll say that this is a cross-sectional area of A. So if we've wound a cylindrical solenoid, then that cross-sectional area is a circle. Okay, so for each turn of the solenoid, we would say, so let's just draw a single turn of our solenoid. So it's a single loop, and it has area A, and there is a magnetic field that is going through this loop that has a value of B is mu naught Ni over L. And remember, one of the nice things about the solenoid was that the magnetic field in its interior was uniform. And so for each turn of the solenoid, we would calculate a magnetic flux would be B dot dA. It's going to be our dA vector and our B vectors are parallel. So B dot dA just becomes B dA. B is uniform, so it's a constant. We take it outside, and we get B times A. But we get this flux for all n of the turns of wire. So this above calculation is just for a single turn of the wire. Therefore, the total magnetic flux, let's do it this way. Let's say that this is the magnetic flux of our solenoid is n times what we calculated for a single turn. And so that's equal to B times N times A. But B, we know, is mu naught N I over L, and I over L. So that's B. And then we have NA. And so the total flux for our solenoid is then mu naught N squared I times A over L. So that's one result that we're going to need for our discussion. Okay, so that's fine. So far, that's kind of everything that we know about a solenoid. And so we can ask it the following question. What is the voltage delta VL across the solenoid? We've calculated the flux, and we know that we could use Faraday's law to calculate EMFs. And so we could use Faraday's law, which told us how to calculate the magnitude of this EMF. It was equal to the derivative of the magnetic flux, and so we're now talking about our entire solenoid. And so that's going to be d by dt of all of this stuff, mu naught N squared I A over L. So mu naught and N and the geometrical factors A and L, they're definitely all constants. And so we could write this as mu naught N squared A over L. And then we could say that what we have left is a di dt. Okay, so one observation is if I is equal to a constant, then di dt is equal to 0, which says that this induced EMF from Faraday's law is equal to 0. So there is no voltage across the solenoid when I is a constant. On the other hand, we were calculating the magnitudes of these EMFs. On the other hand, if I is not constant, then it looks like by Faraday's law that we get a non-zero voltage across the solenoid. Okay, so, however, if I is changing, then I'm going to write this EMF as the voltage delta V across the solenoid. And the subscript L is going to stand for inductance. So we're going to call our solenoid an inductor that has an inductance of L. Okay, well, we've already written down the result. It was mu naught N squared A over L, and then it was the di dt. Okay, and so what is the inductance L? The inductance L is defined to be all of these prefactors. So this is the inductance L. So L of a solenoid is determined by the number of turns or windings of wire squared times its cross-sectional area divided by the length. Okay, so that's fine. Then we would say that the voltage across our inductor is equal to the inductance times this di dt. So I want to see if we can figure out the proper way to write this without having to say it's just the absolute value of the voltage. And so let's go back to our picture right at the beginning. There's our solenoid, and let's suppose that I is increasing such that B, and therefore the flux through our solenoid, are increasing, right? The magnetic field B is directly proportional to the current. There's the expression right there. So if we have an increasing current, then B is increasing. And then the flux is basically B times A times the number of turns of wire. And so if B is increasing, so is the flux. Well, what Lenz's law tells us is that the induced magnetic field opposes that change in flux. And so if the flux is increasing, we're going to get a B induced that tries to oppose that increase. And so it's in the opposite direction of B. So how do we make an induced field in that direction? Well, there must be an induced current, which by the right-hand rule, we put our thumb in the direction of B induced, and our fingers tell us the direction of this induced current. And so there's an induced current, I induced, that is going in the opposite direction of the original current, I, that was said to be increasing. So this is our I induced is flowing counter to the existing current. Okay, now if this was not part of a complete circuit, but just a length of wire, and we put an increasing magnetic field through the coil, then what would happen is we'd get positive charges piling up over here on this end, and we would get negative over here on the other end. And we know that electric fields point from high potential to low potential, so this is the high potential side, in this case, of an increasing current, and this is the low potential side. Okay. So what must happen then is that if we were to try to write down an expression for the voltage difference across our inductor, we said that's going to be equal to L di dt. And in the case of our example, we said that we were going to imagine an increasing current. So if we have increasing current, then di dt is positive. L is just a bunch of constants that are all positive, so that's positive. And so this delta VL, as it's written now, would be positive. And so if we write this as delta VL, so let's write this as V1, V2, so that delta VL is V2 minus V1. So we're going to go across this inductor in the direction of the original current I. Then the final potential is a low potential, and then we're subtracting off a high potential. And so it must be that delta VL, in our case, is a negative number. So the expression that we've written down so far is the product of two positives, and so we require a negative sign to correct that. So that's the voltage difference across our inductor, which is just a solenoid that has inductance L, which is determined by geometrical parameters, the cross-sectional area and length, and the number of turns of wire. Okay, so if you did the opposite, if you said, okay, let's imagine that the current was decreasing, then to sustain the flux that we originally had, we would reverse the direction of the induced magnetic field, which would reverse the direction of the induced current, which would make the voltage difference across our solenoid positive. This expression would still work because if we had a decreasing current, the di dt would be negative. And so we would have minus L times a negative di dt, which would be positive, and that works. And so this works for I increasing or decreasing. In the picture above, we considered the case of an increasing current. Okay, so there's the voltage across our inductor and the inductance L. And we know how much magnetic field it stores. The magnetic field of an inductor is here. So this is a lot like capacitors. So let's compare inductors and capacitors. So if we made a table, we could say let's say we have inductors over here and we have capacitors over here. So our inductors create a magnetic field that's uniform and has a value of mu naught n I over L. Capacitors created an electric field that was uniform, and so let's see if we can remember something about capacitors. C was defined to be Q over delta V, the voltage across a capacitor. But if we had, let's say, a positive plate here and a negative plate here, then we would have an electric field that would point from positive to negative, and the voltage across a capacitor is minus the integral of E dot ds, and so if the distance between the capacitor plates is d, then we're going to get minus E times d. So the electric field is equal to minus the voltage across the capacitor. Actually, let's not do that. Let's just say, therefore, C is Q, and then the voltage across capacitor is minus E times D, or E is going to be equal to Q divided by C times D. But for a parallel plate capacitor, remember C was equal to epsilon naught A over D. And finally, making that substitution, Q is Q divided by C, which is epsilon naught A over D, and then times D. And so therefore our electric field must be of the form Q over epsilon naught A. So a geometric factor, so here I'm just going to calculate the magnitude of the electric field. So the electric field is determined by a geometric factor, 1 over A, and a constant epsilon naught. So it's epsilon naught over A, and how much charge you put on the plates. Our magnetic field is determined by geometric factors, the number of turns N and the length L, a constant mu naught, and how much current we have. So capacitance, we already wrote down, is epsilon naught A over D for a parallel plate capacitor. Parallel plate, let's say. And so we calculated the inductance of our solenoid. We got mu naught N squared A over L. I think that's what it was. Yep. Okay. The voltage across our capacitor. Let's continue our table over here. Inductors, capacitors. The voltage across our capacitor is equal to Q over C, and the voltage across our inductor was equal to minus L di dt. Okay, so I guess that's what we know so far. So let's see if we can extend this a little bit further. So let's calculate some of the properties of inductors and energy. So if you think of the power across a resistor, the power dissipated by a resistor, we calculated that in a few different ways. It was I squared times R, or V squared over R, or it was also voltage times current, the voltage across the resistor times the current through it. So the power associated with a circuit element, whether it's a resistor or a capacitor, a battery, or an inductor, is P is I times the voltage difference. Okay, so let's calculate the power associated with an inductor, and we'll just think about the magnitude. So it's going to be I times the voltage across the inductor. So the voltage across the inductor was L di dt. Okay, but power is also the change in energy divided by the change in time. So how much does the energy change in a time interval delta t, where we shrink that time interval down to be an infinitesimal time? So this implies, if we multiply by dt, that the change in energy is this power times dt, but P is IL di dt, and then we're multiplying by dt. And so we'll get rid of those factors of dt. And so a change in energy associated with an inductance is L I di is what we have remaining. So U is going to be the integral of L I di. And so let's imagine we start from zero current up to some maximum. And so that's going to be L the integral of I with respect to I is I squared over 2, and we evaluate between the limits 0 and I, we get the energy is equal to 1/2 L I squared. So this is the energy stored in the magnetic field of an inductor or a solenoid. Okay, so 1/2 L I squared. So this is UL is 1/2 L I squared. Okay. If you think back to what we did for capacitors, we also calculated the energy associated with a capacitor. And let me see if we can find it here. I want to make sure I don't get it wrong. So the energy stored in a capacitor is the energy associated with that electric field, and it was equal to, one of the expressions was 1/2 Q squared over C. Okay, so that's kind of interesting that there's this kind of very nice analog between our correspondence of kind of what capacitors do for electric fields, inductors do for magnetic fields. So this creates a uniform magnetic field inside, and it also creates a magnetic field. In the case of an infinitely long solenoid, the magnetic field outside would be 0. The capacitor creates a uniform electric field inside, and in the case of like infinitely large sheets for our parallel plate capacitor, the electric field would be 0 outside. The inductor stores magnetic energy, the capacitor stores electrical energy, and so we have expressions for the magnetic field and electric field, and the inductance and the capacitance. Okay, good. So the very last thing that I want to do is to see if we can understand the behavior of a solenoid or an inductor in a circuit. So inductors as circuit elements. Okay, so what we're going to do is we're specifically going to look at LR circuits. So they're going to be circuits that have just a battery and one inductor and one resistor. So we'll also incorporate a switch. So this is a switch S, and then we have a resistor R, and the circuit symbol for an inductor is just a coil, right? So that makes sense because the way you make an inductor is you just take a length of wire and wind it into a coil. Maybe I can make a slightly nicer one. Okay, so this is our coil, and it has inductance L. And so let's say our battery has some EMF. Okay, so initially, the switch is open, and it's been open for a long time such that I is equal to 0. Then we're going to close the switch at time t equals 0. So the question is, how does the current develop over time? We can't have the situation, we can't have a current that instantaneously changes from 0 to some non-zero value. That instantaneously changes from 0 to a non-zero value. Right, so we can't have the situation where if we were to plot the current as a function of time, it's not going to start at 0, and then right when the switch is closed at, say, t equals 0, that it just instantly pops up to some non-zero value. Okay, so that doesn't happen. So what we're going to try to do is we're going to try to figure out how does the current evolve when the switch is closed. So the current must change smoothly. And so, for example, we could ask the question like, what determines how quickly the current is going to change? Okay, so here's the analysis of the RL circuit. Again, it will have some similarities to our analysis of the RC circuit. So we'll just do a loop rule. What we'll do is we'll go back to our circuit. We'll start in, say, the lower left corner, and then we'll just do a loop that returns to its starting point. And so the first thing we do is we cross the battery, and let's imagine that when the switch does close, we get a current that flows from the negative to the positive terminal of the battery. Okay, so the first thing we do is we cross the battery, and so we gain a potential of plus the EMF. Then the next thing we do is we cross the resistor in the direction of the current, and so we lose a voltage IR across the resistor. And then we cross the inductor, and if we've just closed the switch, we would expect the current to be increasing, and we just saw that in that case, the voltage difference across the inductor was negative if we go in the direction of the current. And that makes sense that we would write minus L di dt, because di dt is going to be positive for an increasing current. Okay. So let's think about the initial conditions. Initial conditions are right when the switch is closed, I is equal to 0 at t equals 0, right? We're assuming the current doesn't instantaneously change, so it starts at 0. So that means that at t equals 0, our loop rule looks like the following. We still have the battery voltage, but then we have minus IR, but I is equal to 0, so that part vanishes, so we get minus 0 times R minus L, and then we don't know di dt at t equals 0. We don't know that value, but whatever it is, our loop rule still must be equal to 0, and so therefore we can solve for di dt at the time t equals 0. We just take the minus L di dt at t equals 0, move it to the other side, and then divide by the L, and what we're going to find is that that's just equal to the battery EMF divided by L. Okay, so what we could do is we could say, therefore, immediately after the switch closes at t equals 0, the current changes at a rate of di dt at t equals 0 is equal to the battery EMF divided by the inductance. Okay, so what we're going to do is, let me call this equation star. We're going to return to star. So we're going to return to star, and maybe we should just rewrite it. It was just a loop rule. And this was the loop rule was equal to. Let's make a substitution. X is defined to be di dt. Okay, so if we did that, we'd have battery EMF minus IR minus L times X is equal to 0. And so it's not obvious why we did that just yet, but now the next step is to take a time derivative of our expression. And so let's note the following. The battery voltage, or EMF, is constant, so it doesn't change with time. Its time derivative is 0. D by dt of IR, R is a constant, so we get R di dt, but di dt is what we called X, and so we get R times X. And then the last term, we have an Lx d by dt. L is a constant, so this becomes L dx dt. All right, so therefore, our expression, after taking the time derivative, becomes 0 minus IR, but we've taken the derivative, so it's minus Rx, and then we have minus L dx dt. And that still has to be all equal to 0. All right, so let's try to solve this equation for x. Let's see, we're going to get what? So we'll have L dx dt is equal to minus Rx. Let's multiply by dt, and at the same time, let's make our multiplication factor dt over L. So then we'd get what? Dx is equal to minus R over L dx dt. What we should have done is we should have included a factor of x in there, but never mind, we can do that now. Let's divide by x, and so we have dx over x is equal to minus R over L dt. Let's integrate both sides. What we have is nice now because we have on the left-hand side things that only involve x, and on the right-hand side we just have constants and a time, or a dt. And so we have the integral of dx over x is equal to minus R over L, the integral of dt. And so we'll go from 0 to some later time. And so we're going to integrate this from x0 to some value of x at a later time. But recall, x is equal to di dt. Therefore, x0 is di dt at a time t equals 0. But we've already worked that out as part of our initial conditions. Di by dt at t equals 0 was the EMF divided by L. So this x0 is the EMF divided by L. Okay, so on the right-hand side, this just becomes a t. Over here, we've done this kind of integral a few times now. It's the ln of x, and so we're going to get the ln of x minus the ln of x0, which is the ln of x over x0. So what we have then is that the ln of x over x0 is equal to minus r over L times t. So if we exponentiate both sides, we have the exponential of r over L times t is equal to x over x0, or if we define a time constant tau, say is L over R, then what we can do is we can write that x is equal to x0 e to the minus t over tau, and we know that x is di dt, and x0 was the EMF divided by the inductance. And so what we have now is a solution for how the rate of change of current varies with time. So this is di dt, and here's t. And what this does is it starts at a value of the EMF divided by the inductance, and then it decays exponentially, like so, and tau is somewhere over here, and that's equal to the time L over R. So how quickly the current changes is determined by the inductance L and the resistance R via this time constant tau is L over R. What we could say immediately, well, okay, let's go a bit further, and then we'll see if we can analyze this further. So to go further, we're going to multiply by dt and integrate. So we get di is equal to epsilon over L e to the minus t divided by tau, and then we multiplied by dt, and then we're going to integrate. We said the current would have to start from 0, and then it'll evolve to some non-zero value, and the switch closes at t equals 0, and we're going to find what the current is at some later time t. So this is just I on the left-hand side. So we get that I is equal to epsilon over L at the integral of 0 to t e to the minus t over tau dt. So when we integrate an exponential, we'll get the exponential back again, and then we must pick up also a factor of minus tau. You could verify that that works by taking the derivative of minus tau e to the minus t over tau, and what you should get back is e to the minus t tau. And then we have to evaluate between the limits of 0 and t, which is minus tau at e to the minus t over tau minus e to the 0, but e to the 0 is 1. And so we could write this finally as, let's put the minus sign in front. The minus sign in front, let's put it through. So we'd get minus minus 1 is plus 1, minus e to the minus t over tau. Okay, so what do we have, therefore? The current is equal to EMF divided by L times tau 1 minus e to the minus t over tau. but tau was epsilon, was L over R. Tau was L over R. So when we put in the L over R, the inductance cancels out, and we get I is equal to the EMF over R, 1 minus e to the minus t over tau. So this is the current in the LR circuit after the switch is closed at t equals 0. If we made a plot of this, what it would look like at very long times, a long time after the switch is closed, we'd get e to the minus e to the minus a really large number. And e to the minus a really large number is 0. So the exponential goes away, and we just get the EMF divided by R. So it's like the inductor is not in the circuit anymore. And if you think about that, that makes some sense, because after a long time, you'll have established an equilibrium current, a constant current. And we only get a voltage across the inductor when the current is changing. So if the current is not changing, there's no voltage across the inductor. And when we analyze the loop rule, we would just get the EMF of the battery minus IR, which leads to I is the EMF divided by R. And if you plot this function carefully for times that aren't long, what it ends up looking is something like this. Let me see if I want to draw this up slightly nicer. There we go, something like that. Okay, and the time constant tau is L over R, somewhere around here. At this value, we get the current is epsilon over R, 1 minus e to the minus 1. So E is about 3, it's 2.7. So 1 over E is about a third, 0.33. 1 minus 0.33 is around 0.67. If you put in the correct value, this is about 63% of the total current. So the current reaches 60% of its equilibrium value after a time tau, which is L over R. So if you make L small, so if you had a small L, then tau is small, and that would mean our current would build up quickly. This is small L. If you made tau large, then the time constant would be a large number, and it would take a long time for our current to reach equilibrium. So small L means a fast approach to equilibrium current. And then a large L is a slow approach to equilibrium current. Okay, so the very last thing that I want to do is I want to think about, we won't solve the problem, but I'll just set it up. So what about a circuit that has an inductor, a resistor, and a capacitor? So what that might look like is a battery with some EMF and then we have a switch S, and then maybe we have our resistor, and then we have our capacitor, and then we have our inductor, like so, and then we complete our circuit. This is R, C, and L. And when the switch is closed, we imagine that we start to get a current to evolve that goes from the negative to the positive terminal of the battery. So if we did a loop rule, what would happen? So if we do our loop like usual, start in the bottom left corner and do a full loop, the first thing we do is we cross our battery and gain the EMF. Then we cross the resistor in the direction of the current. Then we cross our capacitor, and then we cross our inductor, and we get back to starting point. So the capacitor voltage, let's see, C is Q over delta VC. So this is Q over C. And then the inductor voltage is L di dt, and that has to be equal to 0. Okay, let's see, I is dq dt, so therefore di dt is d by dt of dq dt, but that's just the second derivative of charge with respect to time. And so what we're going to do is, for the current, we put dq dt. For di dt, we have d2q dt2. And I'm going to reorder some of these terms. So we'll put, actually, let's do it this way. Let's get rid of all the minus signs by taking all of the IR, the QC, the LDIDT to the other side. So then we would have that the EMF of the battery would have to be equal to, I'm going to write first 1 over C times Q. Then the next one I'll write is the resistor, is Ri, but we'll write I as dq dt. And then we have an L, and we're going to have a d2q dt2. And so even though our circuit is relatively simple, it's just 3 components, 1 resistor, 1 capacitor, 1 inductor. The solution for the charge requires that we solve a second order, this is called a second order differential equation. In Q. And what it leads to is pretty complex behavior. We get complex behavior. If you close the switch and you looked at what the current would do as a function of time, what you would find is that if this is T and this is the current is dq dt, after closing the switch, depending on what the relative values of L, R, and C are, one possibility is you get oscillations that are damped. So these are called damped oscillations. And so I won't attempt to try to solve this here, but I'll just advertise that if you were to do a physics degree, one of the courses that you would take is Physics 231. So in fact, if you're a first-year student, you would take that in your second year starting in September. And this is Introduction to Electronics. Okay, and it turns out the exact behavior that you would see for, say, the current after closing the switch would depend on how big your resistance was relative to some of the other components. And so you get either what's called overdamped, underdamped, or critically damped behavior. What I drew is the case for low resistance, which leads to an underdamped set of oscillations. Okay, so if that's something that you think sounds interesting, then you might consider taking some more physics courses next year. All right, thanks very much. That's going to be a wrap for the Physics 121 YouTube videos. I hope you found them useful. I did the best I could to try to make them a convenient resource for you. Keep an eye on the course website for any updates about the final exam and things like that. Okay, thanks very much. Bye.